special relativity concerns time dilation, where the time on the observer's clock is given and the observation of the elapsed time on the clock on the moving spacecraft is given. We're to calculate how fast the spacecraft is moving away from the Earth. We're given that it's moving away from the Earth. And it's done at 1 a.m. 1 a.m. doesn't mean anything. So it's not part of the calculation. It's a distractor. It's the minutes that are important, the 8 minutes and the 17 minutes. So we have the principle in special relativity that moving clocks run slow. If we see a clock moving, the hands of the clock, this is an analog clock, they won't advance as fast. If it's a digital clock, the blink of the seconds, the number change, will not occur as rapidly as for a digital clock on the Earth. So our observer's on the Earth, that's our frame of reference, and we're watching this spacecraft move away. Now, the way that the clocks behave here is that the elapsed time on the rocket is in an expression with the elapsed time, we'll just put T, on observer's clock. Which of these numbers is bigger? The elapsed time on the rocket or the elapsed time on the observer's clock, given the principle that the clock we see moving runs slow? This is the smaller number. In special relativity, there's a calculation factor called gamma. And gamma is equal to 1 over the square root of 1 minus the speed of the object squared divided by the speed of light squared. And this gamma, it's 1 if the velocity is 0, but otherwise gamma is bigger than 1. Gamma is bigger than 1, and the elapsed time on the observer's clock is going to be the bigger number than the time on the rocket. We divide by 2 or 3 or 4, it depends on the speed. We're to determine the speed. What we're given are the times. So we have 8 minutes equals 17 minutes divided by gamma. The time on the moving spacecraft is observed as less advancing of the hands. If this is an analog clock on the rocket. So our procedure here is we're going to get a number for gamma, and then we're going to use that and solve for velocity in terms of the speed of light. I may convert it to meters per second, but let's proceed. So to solve for gamma, I have to multiply both sides by gamma. I have to divide both sides by 8. So 17 over 8. And I get 2.125 for the gamma number. And then the 2.125 is equal to 1 over the square root 1 minus v squared over c squared. We found the gamma by virtue of the times that were given. And now I'll cross multiply here. So I'm going to multiply both sides by this whole square root. I'm going to divide both sides by 2.125, and we get the square root of 1 minus v squared over c squared equals 1 over 2.125. This can be calculated, so let's do that. I kind of work back and forth down the page here. So the square root of 1 minus v squared over c squared, 1 divided by 2.125 is 0.4706. And now we'll square both sides. Our velocity is here under the control of the square root. So I want to square both sides. The square of a square root will just get 1 minus v squared over c squared on the left. And your calculator will tell you that 0.4706 squared is 0.2215. Now I'm going to add v squared over c squared to both sides. I'm going to subtract 0.2215 from both sides. And again, I'm going to come back to my left side here and do this calculation. So I have 1 minus 0.2215 equals v squared over c squared. What should be done next? Instead of taking square root, I'm going to subtract these numbers as a first step. So 0.7785 is v squared over c squared. We want v, we don't want v squared over c squared, so let's take a square root of both sides now and feed that into the calculator, and you get 0.882 for the square root of 0.7785, and you get v over c for the square root of v squared over c squared. Multiply both sides by c, and we get that, I'll put the v on the left side, v equals 0.882 times the speed of light. C represents the speed of light. So is it reasonable? Well, at least it's underneath the speed of light. We can't have a rocket that's moving faster than the speed of light, so this number is reasonable in that sense. If you want to, you can go ahead and put 3 times 10 to the 8th here for the value of c, and multiply by 0.882. So that speed would be 2.65 times 10 to the 8th meters per second. And as a velocity, the direction is away from the Earth. We do not have any rockets that can go this fast, nor near this fast. So in that sense, it's a hypothetical problem, but perhaps someday in the future, rocket technology will advance that will be able to get at least robotic spacecraft up to this speed and do a little bit more exploring. There are 4 spacecraft that have left our solar system. They're in the process of leaving the solar system. 2 Voyager spacecraft and 2 Pioneer spacecraft. The Voyager are the faster of those spacecraft. And if my memory is right, the Voyager spacecraft, none of them are directed towards a nearby star, but if they were, the fastest one, I think it takes about 60,000 years to reach the distance equivalent to the distance to the nearest star. 60,000 years. That's our current technology for rocket flight. And maybe technology is a little better. These were launched in the 1970s, but we're not going to be exploring nearby stars in any time soon unless one of you invents something that helps rockets go faster. But moving clocks run slow. Remember that principle. There's a factor of gamma that is used in special relativity calculations. The shorter time is the time elapsed on the rocket. Gamma is always bigger than 1 for systems that are moving. And then use the gamma, do some algebra, and you come up with the speed 0.882 times the speed of light. And it's traditional to leave it at 0.882 times c rather than put it into meters per second. But do whatever your instructor would like you to do for that, and keep practicing, of course.